Welcome to Math with Professor V. In this video, I will be working through and solving more linear differential equations. If you need an introductory video lecture on this lesson, I will link it in the description, but I'm just gonna breeze through the overall process and start solving more examples just to help you guys get through your homework assignments and whatnot, okay? So a differential equation of the form a sub 1 of x dy dx plus a naught of xy equals g of x is said to be a linear equation, and the standard form is right here. We rewrite it as dy dx plus p of x times y equals f of x. And the steps to solving a linear differential equation involve writing it in standard form first, finding the integrating factor, which is mu of x, it equals e raised to the integral of p of x dx. Then we multiply both sides of the equation by the integrating factor, rewrite the left-hand side as the derivative of the integrating factor times y, and then integrate both sides and solve for y. I know I went through that quickly, but the point of this video is not to give you a whole lesson. I have a whole nother video that does that. I just want to jump in and solve examples. Now, one thing I do want to point out is that when we are solving these linear differential equations, we're often asked to give an interval on which the solution is valid. And in order to do so, you want to check where both p of x and f of x are continuous. That's how you identify the interval. And so we're going to be addressing that as we solve or work through all of the examples. I have 5 picked out for you, a little bit on the medium to spicy level, okay? If you love this video, I'll do another 5, okay? So directions say find the general solution of the given differential equation and then state an interval on which the general solution is defined. So first things first, I need to put this in standard form. It's not. And I'm telling you right now, these are linear differential equations, but you do want to check, if you're not given that sort of instruction, is it separable? Is it homogeneous? Is it exact, etc., etc.? Okay. Let's see if we can put it in standard form. Let me divide by dx on both sides first, and then also divide by x. I think we can handle doing both, yeah? So dy dx equals x sine x minus y over x. And then, okay, this is looking good. So I have dy dx equals sine of x minus y over x. And remember, standard form is dy dx plus p of x times y equals f of x. So we're almost there. Let me move over y over x. And then now I have dy dx plus, for simplicity, I'm going to write this as 1 over x times y equals sine of x. Okay. From here, let's identify the interval on which the general solution is defined. So here is p of x. Here is f of x. I know I have a restriction here on p of x. X cannot be 0. I need to define an interval on which this solution will be well defined. So excluding 0, I could either go from negative infinity up until 0 or from 0 to positive infinity. What's usually easier is to choose positive values of x. So we're going to choose the interval from 0 to infinity. And then I have no restrictions from sine of x. Sine's domain is all real numbers, so sine of x will be continuous on this interval as well. Good? Okay, now let's go ahead. Let's find our integrating factor, mu of x. Some books call it I of x. It doesn't matter. It's e raised to the integral of p of x dx. So it's e raised to the integral of 1 over x dx. So this is going to be e raised to the natural log of the absolute value of x. We don't put plus c when we find the integrating factor. We don't need to. And then remember, we're already saying x is positive. X is from 0 to infinity, so I don't have to keep the absolute value. So I just have e to the ln of x, which is x. Good? Okay, now what do? You come back to that standard form right here, and you hit everybody with the integrating factor, like they're on the Oprah show. It's like, you get an x, you get an x, you get an x. Boom. Plus 1 over x times x will cancel. And then on the right-hand side, we have x sine x. Good? Okay. The left-hand side better be the derivative with respect to x of y times the integrating factor. And I always recommend you check because I have caught many a boo-boo in my time. So let's make sure this is correct. Derivative with respect to x of y times x, we're going to need to do the product rule. Derivative of y with respect to x, dy dx. Leave this guy alone. Beautiful. Plus, leave y alone. Derivative of x with respect to x is 1. Yes, fab, fab. Now we can go ahead, integrate both sides with respect to x. And let's see what unfolds. So left-hand side, that's the relaxing side. If we're integrating with respect to x, the derivative of some quantity with respect to x, we're just going to get back that quantity. We're just going to get back y times x. And then now we need to take the antiderivative of the other side, x sine x dx. So we need to use integration by parts. I'm going to use Tabular because why not? It's so quick. So x is going to be d, I is sine x. Differentiate until you get 0 in the left-hand column. So 1, 0. That means I need 2 antiderivatives. So this would be negative cosine x, 1 more negative sine x. And then we take the diagonal products. Remember, we have to add an alternating sign component. So the first one doesn't change signs, but the second one I'm going to add an extra negative. So over here we have now the antiderivative is negative x cosine x plus 1 sine x plus c. And then in this case, it is easy to solve or isolate y. So let's go ahead and divide everybody by x. So y equals, let's put the positive term first, right? So it looks better. Sine x over x minus cosine x plus c divided by x. C divided by x does not become a new constant, right? Because x is variable. So you still have to write c over x. Don't redefine it. I just wanted to point that out. And then let's remind the people x has to be greater than 0. That's what we chose. Okay, how was that one? Fun? This was a homework problem for my sweet little class. Okay. Here's another. We have 1 plus e to the x dy dx plus e to the x times y equals 0. I want to point out this differential equation is both separable and linear. I solved it both ways, but I'll just do the linear method for you now. Let's see. To get it in standard form, I need to isolate dy dx. So let's divide everybody by 1 plus e to the x, and then I think we'll be there. Do you know what I mean? So dy dx plus e to the x over 1 plus e to the xy equals 0. So right here, this is my p of x. This is my p of x. And then f of x is just 0. Do we have any domain restrictions? No, it looks like we're good to go on all real numbers. Negative infinity to infinity. Okay. So let's go ahead, let's find our integrating factor mu of x, e raised to the integral of e to the x over 1 plus e to the x dx. Okay, how would you tackle this integral? You could do a couple little techniques. I think the easiest is just a u sub. Let's let u equal 1 plus e to the x. du would be e to the x dx, which we have right here, yeah? Oh, that looks nice. So this is e raised to the integral of du over u. So that antiderivative is going to be ln, absolute value of u. U is 1 plus e to the x. That's never negative, right? So I could just switch that to parentheses. So this is 1 plus e to the x. Now this will happen on occasion. So now I have to go back here and multiply everything by my integrating factor. Well, guess what? You get back the original equation that you had. So we just did a bunch of nothing right now. And what does that tell you? We've wasted minutes of our life that we'll never get back. I know. So how can we avoid having this happen to us again? If you want, it might be a good idea to always check, is the left-hand side already the derivative with respect to x of y times the this quantity here, which we would say, is that my integrating factor sitting there sneakily, not telling me that it's sitting there? So you could check, is this the derivative of y times whatever you see right here? Yes? 1 plus e to the x in this case. And check, look. Derivative of y dy dx, leave the integrating factor alone, plus derivative of the integrating factor would just be e to the x because derivative of 1 is 0, and then we leave y alone. Yep. So if you want to just from now on always check, is this the case? You could. So that way you don't do all this, okay? Anyways, let's carry on. Let's integrate both sides and try not to be too depressed that we wasted some time. And now we have here on the left-hand side, just 1 plus e to the x times y equals some constant, right? Antiderivative of 0. And then get y by itself. So you have c over 1 plus e to the x. And then x can be any real number. Or you could write the interval from negative infinity to infinity. Whatever your heart desires, please do it. Okay? Actually, no. Do what your instructor wants if they have a preference. I retract that. Okay. All right, example 3, we have y dx plus xy plus 2x minus y e to the y dy equals 0. Now, I wanted to do this example because if we try to put it in the typical standard form that we've been using, we get stuck. So if we try to put it in dy dx plus p of x times y equals f of x, we're going to run into some problems. So let me show you what happens. If this is our goal, I would want to divide everybody by dx, right? So then you'd have y plus xy plus 2x minus y e to the y dy dx equals 0. And then hopefully now you're already seeing, here's the big issue. We have this e to the y. We're not allowed to have any functions of y in a linear differential equation if we treat x as the independent variable. You can have p of x times y to the first, that's what makes it linear, but you can't have this e to the y situation. So then you go, abort mission. Let's still set it up as a linear differential equation, but this time we're going to treat y as the independent variable. So our derivative would be dx dy. Then we'll have, let's call it p of y times x equals some g of y. Right away, you could have noticed that that was going to be a problem, this e to the y. So we got to switch things up. So now let me divide this entire equation right here by dy. And let's see what we got. So I have y times dx dy plus xy plus 2x minus y e to the y equals 0. Okay, I'm going to want to divide by y. And then also keep all the terms that have x over here. Move this guy over there. So dx dy plus, this is going to be x plus 2 over y times x equals e to the y. And then now we're pretty much there. So dx dy plus, if I factor out the x, then I have 1 plus 2 over y equals e to the y. So boom, right here, this is my p of y, and this is my g of y. P of y, g of y. Good? All right, let's decide now on what interval our solution will be valid. P of y, notice y can't be 0. No restrictions for g of y. So let's pick the interval from 0 to infinity. Sometimes you'll see it written like this. That way it's specific that this interval belongs to y and not x in this case, right? So you could write that. If you write interval notation, then we don't know if it's for x or y, but whatever, either one's fine. Beautiful. So now let's go ahead, let's find our integrating factor. So mu of y this time, it's not mu of x, is e raised to the integral of 1 plus 2 over y dy, which is going to be e to the y plus 2 ln absolute value of y. And then from here, what we're going to do, because I want to simplify as much as possible, let's split this up into e to the y times I can move this to make it the exponent on y. I don't need absolute value because we're on the interval from 0 to infinity anyways. E to the ln y squared. And then this ends up giving me y squared times e to the y. So that's my integrating factor. So now I'm going to come back right here, hit everybody with the integrating factor. Okay, so we've got now dx dy y squared e to the y plus x times, you guys, I'm going to multiply the y squared through here, and then it's going to become y squared plus 2y e to the y equals, and then over here on the right hand side we'll have y squared, and then e to the y times e to the y is e to the 2y. Beautiful. So let's double check, is this the derivative with respect to y this time of x times my integrating factor? Double check before you proceed. So let's see. Derivative of x with respect to y, dx dy, leave this alone. Now I need to differentiate this with respect to y, and we would need to do the product rule. So derivative of y squared is 2y, leave this alone. There it is. Plus, leave y squared alone, derivative of e to the y is e to the y. There it is. And then leave x alone. Perfect. Look at us, we can't mess up. dy. Are we good? Okay, on the left, now we've got x times y squared e to the y equals, what would you do for this guy? I would definitely utilize tabular or the DI method of integration by parts. So here we go. I'm going to differentiate the polynomial, and then I is e to the 2y. So this is 2y, 2, 0. Antiderivative here is going to be 1/2 e to the 2y, 1/4 e to the 2y, and 1/8 e to the 2y. Good. Then we take the diagonal products, and then don't forget we have to add alternating signs. So plus, minus, plus. And here we go. Antiderivative is going to be 1/2 y squared e to the 2y minus, we've got 2 times 1/4, so that's also 1/2 y e to the 2y plus 2 times 1/8, so that's 1/4 e to the 2y plus c. And then let me try to isolate x now, right? That's my dependent variable. So I'm going to divide everybody by y squared e to the y. Is it going to come out nice? I hope. So x equals, 1/2. I'll have e to the y, right? Because e to the 2y divided by e to the y gives me e to the y. Minus 1/2y. Remember, I'm dividing by y squared e to the y. Plus 1/4y squared e to the y. Plus, this would be c over y squared. You could put e to the y down there. Let me just put e to the negative y so that all the e's are on the top and the y's are in the bottom. This looks cute. And then remember to tell everybody y is greater than 0. You could put, in the back of the book, they put between 0 and infinity, but this is enough. Okay? This is beautiful. My heavens, I think I would like to put this on an exam one day. All right. Shall we do a couple more? Let me make sure I wrote this one down correctly. The last one, I had to pause the video because I wrote it down wrong and I was wondering why things weren't working out. No, it's good. We're good. Here we go. We're already in standard form, are we not? Yes, we are, Professor V. So, p of x is 1. This is f of x. On which interval are they both continuous? It's looking like all real numbers to me, guys. It is indeed. Okay, let's find our integrating factor. E to the integral 1 dx, which is going to be e to the x. How cute. Okay, so let's multiply everybody now by e to the x. So we've got dy dx e to the x plus y e to the x equals. I'm just going to multiply through by the numerator here. It's going to be e to the x minus e to the negative 2x times e to the x is e to the negative x over e to the x plus e to the negative x. Good? Okay, let's check. Is this truly the derivative with respect to x of y times the integrating factor? Are you checking? Yes, it is. Okay, good. So then now we're going to go ahead, integrate both sides with respect to x. Now I got a little excited when I saw the right-hand side and I started thinking of my hyperbolics. But at the end of the day, when we want to write out the solution to our differential equation and have y in terms of x, it's best to just stick with the way things are, because then we already have everything in terms of natural logs and whatnot. I don't know if you remember your definitions for the inverses and this and that, so it's just easier if you want to leave it. Okay, so we've got over here y times e to the x equals, and then now how to integrate that right-hand side. We can just do a u sub. Let u be the denominator. Oh yeah, let u be e to the x plus e to the negative x. Then du is e to the x minus e to the negative x dx. Oh me, oh my, that's sitting right here. So then I've got integral du over u, love it, which is ln absolute value e to the x plus e to the negative x plus c. Okay, now let's think. This quantity here is never going to be negative, so I don't need to keep the absolute value bars. So we have y e to the x equals ln e to the x plus e to the negative x plus c. Let's divide by e to the x. You could put it in the denominator. The back of the book just has it as e to the negative x multiplied by all of this. Okay, plus c e to the negative x. And then let's remind the people x could be any real number. We had no restrictions on the interval for our solution. Good. Are you having fun now? I hope so. I've got one more for you. I can do another video, so don't be sad. If you were like, keep them coming. I could solve differential equations all day. I know how you feel. I love them so much as well. See, any reason why we would think this is not going to be our typical dy dx differential equation? Oh yeah, this y squared over here ruining things. So it's not a linear differential equation treating x as the independent variable. Instead, we're going to have to switch it up, do it the other way. So dx dy plus p of y times x equals g of y, okay? So on that note, let's divide everybody by dy. So y times dx dy plus x plus 2xy squared minus 2y equals 0. From here, divide by y. So we've got dx dy plus x over y plus 2xy minus 2 is 0. And I want to have everything times x on one side, and then over there is going to be my g of y. So I have dx dy plus, let's factor the x out, and then now I have 1 over y plus 2y equals 2. This is my p of y, and this is my g of y. Let's decide what interval we're on. P of y is restricted when y is 0, so let's say y has to be between 0 and infinity, okay? Good. Now let's find our integrating factor, mu of y, e to the integral 1 over y plus 2y dy. This is going to be e to the ln absolute value of y plus y squared. And then we know we don't need the absolute value on y because y is already positive. Good. So I can write this as e to the y. No, excuse me. So I can write this as e to the ln of y times e to the y squared, which is going to give me y times e to the y squared. Ooh, what a cute integrating factor. Okay, come through, multiply this by the integrating factor. So we've got dx dy, y to the y squared plus, I'm going to run this y through this quantity so it cleans up. So I'll just have x times e to the y squared and then already multiply the y through there. Do you know what I mean? Oh, good. X e to the y squared times 1 plus 2y squared. And then this equals 2y e to the y squared. Okay, beautiful. This should be the derivative with respect to y of x times my integrating factor. And you can check it indeed is. And so we can integrate both sides now with respect to y. Okay, do we need to do by parts on the right-hand side? No, we can just do u sub, and perhaps you can do the u sub in your head, right? If you let u be y squared, du is 2y dy. I encourage you to do this in your head. So on the left, we'll just have x times y, e to the y squared equals. The antiderivative of e to the u was e to the u, and u was y squared plus c. If you're in my class and you just do this all in your head, I'm so happy. I'm not mad. I'm excited for your future, okay? And then from here, can we get x by itself? Divide by y, e to the y squared, we sure can. So then x equals 1 over y plus c over y e to the y squared. Do we like that? Sure. Typically in the back of the book, they're writing the exponential functions with negative exponents instead of in the denominator. So I'm pretty sure if you double check back there, it's 1 over y plus c over y e to the negative y squared. And then y has to be greater than 0. How do you feel about that? Yeah, okay, we can discuss in class. Or in the comments if you're not in my class. Or if you're in my class, talk in the comments too, I don't care. Anyways, I hope you enjoyed the video. If you want more examples, let me know. I can keep doing these. I'm doing some homework and some non-homework problems. I just thought the more exposure, the better. Differential equations is like a trickster class, right? So you learn the concepts, but also you just gotta be a computational beast and crank them out. And the best way to get to that level is to practice in a somewhat obsessive fashion. I love all that stuff. Hopefully you do too. And if we solve together, maybe it'll get you excited and hone your skills. So that's all for now. Don't forget to give the video a thumbs up, subscribe if you haven't already. Follow me on Instagram, TikTok, Math with Professor V, and I will be back sooner than later. Let me know what kind of stuff you want. Okay, love you all. Bye.